Hi everyone, today we will discuss hydrogenation reactions. So, as we were trying to discuss in the last class, I think we have discussed quite a lot about the fundamental reactions of organometallics, but time has come to apply some of this knowledge into the real catalytic cycle and see how best we have understood those simple techniques. I think hydrogenation is one of the simplest reaction, of course a very effective reaction as all of you may be familiar with, but hydrogenation reaction as well utilizes these simple reaction techniques which we have discussed so far. Hydrogenation catalysts are well known to many of you. If you look at very carefully, there are two classes of hydrogenation catalyst. One is monohydrate, another is dihydride. Now, monohydrate catalysts are the one which has one hydride with the metal center to start with. So, the catalyst itself will have one hydride in it, that is the starting material. So, metal ligand complex and metal along with it a hydride is there, that is the monohydrate complex usually all we see. Now, dihydride catalyst by definition should be having two hydride with them when we start. In fact, it does not have any hydride to start with, but in between of course it will have two hydride which can be utilized further. Let us try to look at the monohydrate catalyst first for the hydrogenation reaction, and then we will get into the dihydride catalysts. So, the hydrogenation is the today's topic. As we were trying to discuss, two classes are possible. One is monohydrate and another would be definitely dihydride. Now, in terms of monohydrate catalysts, starting catalyst has one hydride. For example, this ruthenium complex, okay. We can have also other rhodium complex similar to that. We can have a series of these different complexes where these monohydrates are present. Now, example includes these type of example. We have seen that a olefin for instance can be reacting with a hydrogen gas where this this bond dissociation energy is 104 kcal per mole, that is quite high. In presence of this rhodium catalyst, we will be getting overall the saturation of this molecule. So, this hydrogen both the hydrogen can be inserted into this molecule. So, these are the example of monohydrate catalyst where we have seen very clearly that olefin, for example, in this case olefin is reacting with hydrogen, two hydride or two hydrogen atom are getting incorporated into the olefin from an unsaturated molecule. Now, we have a very clean and clear saturated molecule. This is done by a monohydrate catalyst. The reaction mechanism we now need to look at how these reactions are occurring for the monohydrate catalyst. The catalyst we were taking was the rhodium one, this rhodium catalyst which is a 18 electron complex. Please try to count, it is an 18 electron complex. Now, this species undergo first will be the ligand dissociation. What we are going to look at is the saturation of the olefin to give you the alkane. The first step is ligand dissociation. The ligand that can get dissociated pretty easily in this case is triphenyl phosphine from an 18 electron complex. Therefore, you are going to get a 16 electron complex. So, that is the first principle we have used. So, 18 electron goes to 16 electron, one ligand dissociation occurs which we have discussed earlier. So, first principle we have discussed. Now, next would be the olefin coordination. Okay, then again another step, ligand dissociation, olefin coordination. So another fundamental step occur, one followed by second one. Second fundamental step occurs. So we have rhodium hydride to start with, and olefin coordination. Let's not draw all other ligand with it. Okay, so of course all other CO and bis triphenyl phosphine is present. We are not going to draw it too far. Then subsequently, what you can imagine, of course, now by looking at this, you should be very quick in understanding what is happening from there. Is beta migratory insertion, which we have discussed quite extensively previously. So you are going to get this intermediate where at the beta position, alpha beta position, this hydride is getting incorporated. So this is going to be your beta migratory insertion step. Now from this beta migratory insertion step, a hydrogen will oxidatively add to give you this intermediate where you are going to get a metal alkyl intermediate, right. From there on, it's a reductive elimination. So this is going to be an oxidative addition. We have seen ligand dissociation, olefin coordination, beta migratory insertion, oxidative addition, and finally we are going to see a reductive elimination to give you the product where these hydride are going to be part of it. Okay, so this hydride, all these hydrides are now being taken up. So the one of the hydride, that is the one at the beta position, is the one at the beta position. So this is the beta position hydride starting from the metal hydride intermediate. So this is the beta hydride, and that one at the alpha position is coming from the hydrogen gas. Of course, it regenerates, then it regenerates the catalyst, or so to speak, this catalyst, it regenerates. So this is not the material, it regenerates this catalyst, and the catalytic cycle goes on. So what we have seen again in this case is very clearly starting from a rhodium material, starting from a rhodium complex, which is 18 electron species. Therefore, you cannot have a direct association of olefin usually. You need to do a ligand dissociation. 18 electron species undergoes 16 electron species formation. Now you have the space available for an olefin to interact with this metal center. Subsequently, olefin coordination occurs. After ligand dissociation, olefin coordination occurs, and then the hydride, the metal hydride, which we have started from the monohydrate catalyst, the hydride attacks on the olefin as to give the beta migratory insertion step, and subsequently an oxidative addition of hydrogen gas occurs to give you an intermediate, which upon reductive elimination can give you the final product, that is the alkane product. So olefin is getting saturated one hydride at a time. First hydride came from the metal hydride we started from, the second hydride came from the hydrogen gas. In effect, we regenerate the active catalyst to create the catalytic cycle. So catalytic cycle keeps on moving, and we keep on forming the product. Starting from olefin, then olefin and hydrogen gas, by the help of rhodium hydride intermediate, we can get a very efficient catalytic cycle where olefin is getting effectively saturated by hydrogen gas, and that is going to be a beautiful process in making, and it has been utilized quite efficiently for industrial as well as academic use. And this step, this is a monohydrate catalyst once again, because the starting material is having one hydride itself. We will discuss the dihydride catalyst soon, then you will be able to see the difference between the monohydrate and the dihydride catalyst. Monohydrate catalyst delivers one hydride to the olefin first, and then the second one is getting delivered by the hydrogen gas. In effect, in longer run, both the hydrogen, you can say that it is getting contributed by the hydrogen gas itself. So the ligand dissociation, olefin coordination, beta migratory insertion, oxidative addition, and reductive elimination, almost a lot of steps which we have discussed earlier is coming into effect in this catalytic cycle. We will see again and again and again that all these fundamental steps what we have discussed so far will be part of the beautiful reaction. Some of them are really popular. These are very simple as long as you can understand the fundamental reaction mechanism of the organometallic chemistry. Now, let us try to look at the dihydride catalyst. Now, before going into that, let us try to look at one more time at the monohydride catalyst. This is the monohydride catalyst. Want to start with, one of the ligand gets dissociated, and from there olefin coordination occur, beta migratory insertion, alpha beta migratory insertion occur, hydrogen gets oxidative addition into it, and finally the reductive elimination between this hydride and this alkyl, this part, to give you the product formation, alkane product. Along with it, the rhodium catalyst that is getting regenerated is the 116 electron species, which is ready for the next catalytic cycle. Of course, our next topic would be the dihydride catalyst. Okay. Now, dihydride catalyst you have seen a lot. These are the one which are more popular in terms of hydrogenation chemistry. There are name catalyst like Strock-Osborne catalyst, Wilkinson catalyst, and of course Crabtree's catalyst, which are all of dihydride catalyst by nature. Let's try to discuss dihydride catalyst. Dihydride catalysts, right? So we have a 16 electron species, for example, rhodium chloro triphenyl phosphine species, also known as Wilkinson catalyst, of course, Wilkinson's catalyst. Other one, it could be a 12 electron species, rhodium L2 plus. This is a Strock-Osborne catalyst, Strock-Osborne catalyst. And we also have other one, for example, iridium L2 plus. Of course, this is a Crabtree's catalyst. Crabtree's catalyst. Now, for example, very simple one, rhodium chloro triphenyl phosphine 1, the one we call it hydrogenation catalyst. This is very good for mono and disubstituted olefin. What is important to understand that all the hydrogenation catalysts are not going to be effective for all the type of substrates. There are some catalysts which is going to be very useful for a variety of substrate, but then certain other problem could be there. But then there are other catalysts which will be useful for a particular type of substrate, and mainly because it is very expensive or very difficult to deal with. For example, some catalyst will be used only when a disubstituted or a trisubstituted olefin is there. So, if it is sterically crowded, we use one type of catalyst. If it is not sterically demanding, very simple olefin, then we use another type of hydrogenation catalyst. It's all about robustness and reactiveness, and then of course then other factor would be how cost effective these catalysts are. All of them what we are going to discuss are going to be the hydrogenation catalyst. So, they effectively hydrogenate the olefin to give you the corresponding alkane species, but mechanism will be quite similar, but nonetheless they are not used in academics or industry at all the time. All the catalyst, only a particular catalyst usually people try to use for a particular type of substrate. And of course, there are few catalysts which can overcome all the limitation of the reaction, and therefore can be widely used, like universal hydrogenation catalyst. Okay. Now, let us look at the reaction mechanism with our Wilkinson catalyst for the hydrogenation reactions. So, mechanism for Wilkinson catalyst. We start with the rhodium species, rhodium chloro species with triphenyl phosphine as the ligand. Of course, ligand dissociation is the first step. Although it is a 16 electron complex, still ligand dissociation is the first step, and to give you the 14 electron species, and which is actually going to be the one of the key intermediate involved for this process. In this particular case, you get oxidative addition with hydrogen gas first. Just to tell you that neither of these starting material, this is the starting material, it has any hydride in it, but after ligand dissociation, that means one of the triphenyl phosphine comes out, this hydrogen gas comes into the picture to give you the active catalyst. This is the one which is the dihydride catalyst. The name dihydride catalyst is coming because the oxidative addition happens in the first step. In the monohydride catalyst, you have seen that the monohydride one, which is coming with the starting material, is getting inserted with the metal center first, and then oxidative addition is happening into the hydrogen gas. In this case, we see that oxidative addition is happening quite efficiently at the beginning, and subsequently rhodium, this hydride intermediate interact with the olefin. So, this is now then olefin binding. Olefin binding occurs. Subsequently, again, so this was 14 electron species, this was a 16 electron species, then this was an 18 electron species. You can imagine why these 16 electron starting material undergo 14 electron, then 16 electron, then 18 electron. If this ligand dissociation was not there, this step, then this intermediate would have been 20 electron, right, which is not going to be feasible. Therefore, although it is a 16 electron species, it will undergo a ligand dissociation in the overall process to give you the very good reaction. Now, then from there on, this hydride will attack. So, that we were discussing as earlier, beta migratory insertion. This is going to be your beta migratory insertion, oxidative addition, olefin binding, beta migratory insertion to give you the rhodium alkyl anhydride intermediate, where we see very clearly this is forming the final product, and that is going to be your hydrogen over there. So, 2-hydride is getting incorporated into the molecule. These are the 2-hydride, these are the 2-hydride, all these hydrides are coming from the hydrogen gas. Okay. Now, none of these steps, what we have seen so far is, none of these steps is spectroscopically characterized. Okay. Of course, one should also remember that if there is a observed intermediate into the catalytic cycle, that is not necessarily one of the steps for the reaction. So, what in this particular case, in Wilkinson catalyst case, although none of these steps are spectroscopically characterized, still this is a feasible, these are the feasible steps. But in some cases what happens is, let us say you are doing a catalytic cycle, one of the steps you are able to get the crystal structure of, you are able to interact, or you are able to find that you can characterize perhaps one of the intermediate, but that intermediate not necessarily has always to be the one which is associated with the main catalytic cycle. It could be the off cycle intermediate, it may or may not be relevant to the catalytic cycle. So, even if you have a crystal structure from a reaction mixture, there is no point in thinking that that is the one which is participating into the catalytic cycle. You need to test the catalytic competency of the reaction, that means whether that intermediate is giving you the product what you are getting, and kinetic competence, that means that that intermediate should be at least as fast as the original reaction. If these two criteria are fulfilling, both the chemical competence and the catalytic chemical and the kinetic competence, then perhaps you can say that this is the intermediate that is likely to be involved into the main catalytic cycle and one of the component of the main catalytic cycle. One must be very careful in assigning that. But coming back to the hydrogenation reaction, so we have seen monohydride catalyst, and now right now we have seen the dihydride catalyst, and the classic example is the Wilkinson catalyst. It does not start with 2-hydride, but after ligand dissociation it undergo oxidative addition, which it gives its 2-hydride. So, the name came from that step, that it undergoes this oxidative addition to give the dihydride species, but in the monohydride species we start with a 1-hydride intermediate. But the dihydride species we do see very clearly that after ligand dissociation, oxidative addition, olefin coordination and beta migratory insertion and subsequent reductive elimination will give you the product. So, it's a once again these are very simple and fundamental reaction mechanism, and it occurs quite efficiently for these cases. Now, we will look at the stereochemistry of these reactions. If you are particularly looking at one of the example, in this case this one, and you react with D2 with Wilkinson catalyst, what you get is a cis isomer from there on, right. So, this is a cis isomer. So, one diastereomer is forming, one diastereomer is forming, this is cis addition is going on, and therefore, we are going to get only one product in this case, and this clearly demonstrates that cis addition is happening in these cases. Of course, other type of catalyst we will be discussing subsequently, like Strock-Osborne catalyst and of course, the Crabtree's catalyst. So, the take home message for today's class is very simply, we started with the hydrogenation reaction. This hydrogenation reaction is actually the application of all the fundamental reaction that we have discussed so far. So far we have discussed oxidative addition, reductive elimination, ligand dissociation, and coordination of certain unsaturated molecule, and then internal attack, beta migratory insertion, and so on. All these fundamental steps are utilized in these hydrogenation catalysts, and therefore, we both in the monohydrate catalyst and the dihydride catalyst, whatever mechanism we have seen so far, it utilizes these fundamental steps of organometallic chemistry to give you the product. The net result in these cases is the saturation of the unsaturated olefinic molecule to give you the alkane compounds. And as you see, particularly for the dihydride catalyst, we have discussed for the Wilkinson catalyst, we have seen that hydrogen addition, dihydride addition, or is cis in nature. So, it's going to give you the cis product from the dihydride complex. In the next class, we will discuss more about these hydrogenation catalysts, specifically about the dihydride catalyst, Strock-Osborne and Crabtree's and other catalysts, and we will discuss further from there on. Till then, I would like to ask you to read more about the hydrogenation catalyst and get back to me if you have further queries. Thank you very much.